Hey, Jeff Disher here again. Today I'm going to talk about merge sort. This is the talk that I've been leading up to with some background of like recursion and sorting basics in some previous talks. So the highlights of a merge sort algorithm. First of all, it's one of the kind of fast algorithms in the sense that it's an O n log n runtime, similar to things like quicksort, for example. It has an O log n storage overhead. This is because you actually have to allocate additional information each time you kind of go through and try and merge another sublist. This is something you can constrain really tightly if you need to, but in general, the actual storage overhead of most algorithms and most implementations of quicksort is O log n. It's a stable sort. Now, it's possible to actually write an implementation of merge sort which is not stable, and there might be reasons why you'd want to do that, but typically that's not the case. In pretty much any conventional implementation of this, you're going to end up with a stable sort, as in elements which will end up in the same place in the result. They're not rearranged from their relative position within the input. So it's also possible to build an in-place version of this, which means that you don't need additional storage for the output. But that's not really used much in practice. It turns out that the overhead cost in doing that is actually quite prohibitive, and usually there's not really a problem with allocating your additional storage output. One of the really interesting elements of merge sort in the modern age is that it's very easy to make parallel implementations of it. This is really good when you're worrying about, okay, CPUs don't get faster, but you just keep getting more of them. Well, you can actually do sorting of sublists on different CPUs if you want to. And it's even possible to distribute this over like a network or a farm of machines, or a grid, as they're often called. You can do a partially online version of this sort. Usually that's not done, though. The problem is that you need the input that you're reading in small pieces to be roughly the same size as the data that you've already received, because you're always wanting to try to merge lists that are roughly the same size. If you merge a list that has one element and one that has 100 elements, you're looking at 101 things. And if you keep merging one at a time, this is really, really bad. It's just easier to do an insertion sort in that case. But if you're getting things like, okay, there's 10 elements in the list and I just read 10 elements, well, now you're getting only 20 operations to sort the new 10 elements. So it's actually worth doing it in that case. So this is something that is possible, not often used though, because it requires that you know enough about what your input's coming in like in order to bother using it. And one of the great features about this, and why historically it was used a lot, why it was the only real way to do some of these things, is that it doesn't require random access. This was really great historically when merge sort was used to sort pieces of data which were too large to fit in memory. So what they would do is store them on big reels of magnetic tapes and run those into the computers. Well, what it could do is, since merge sort works by always looking only at the one element after the one you just looked at, this was great because it meant you didn't have to read the entire tape into memory. You just read little parts of the two input tapes and your one output tape, and you do the merge that way, and it worked really, really well. So this was something which was really important historically. Today it still has implications in large database merges and such. Large database sorts, rather, they might be larger than the amount of data you can store in memory at once, so that can be a bit of a problem, a reason why you wouldn't use something like a quicksort. But also, certain kinds of data structures actually work this way. Things like linked lists, where you can't just get a linked list and say, okay, I want to jump into the 100th element of it. But no, that takes 100 operations, because you have to go through each other one first. So merge sort works really well in data structures like that, because you're only ever looking at the next one. So to kind of give a more concrete explanation of how this works, what is actual merge sort? What is the algorithm itself? Well, it's based on the idea that you have what's called a top-down pass, or a top-down implementation, where what you're doing is taking one list and splitting it into sublists, and then the bottom-up part where you're merging the sublists together in a sorted fashion. Now, in actual fact, the top-down part is usually not needed. Usually you can just implicitly state that you know how the sublists are first formed. But depending on the implementation of the underlying storage, you might actually need to go through these to build these lists first. But usually it's not really that big part of the algorithm. The important part is the merging phase. So here's an example of this, where we're going to take two sublists that are each 4 elements long and sort them into one master list that's 8. This operation is performed at every level of the merge sort, and the only requirement that it has is that each of the sublists it's sorting are already sorted. The kind of base case for this, if you want to look at it in a recursive sense, is that a list with one element in it is always sorted, which is obvious. So here, walking through how this works. First of all, we've got our output pointer or input pointer in the two sorted lists. So we're going to compare 1 and 2. 1 is smaller, so we write 1 into the output, and now we step ahead. Now we compare 2 and 4. 2 is smaller, so we step ahead again. 3 and 4, 3 again. Now 4, 5, 6, 7, and here we're finished with the list on the right here. So it means that we'll continue consuming whatever is left over from any remaining lists. So in this case, there's just the 8 left in the last one. So we consume that, and the sort is done. And we've performed the merge operation, and all it took was a linear pass over each piece of data. Now, how does this actually work in practice, and why is it not a linear time algorithm if that's the case? Well, it's because you do this over and over again. So to look at how assuming that we know how merging itself works, well, how does the bottom-up implementation actually work? Well, you'd start out with a list like this, where each element is its own sublist, which is sorted by definition because it's one element each. So then what we do is we merge those into 2-element sublists, and then those into 4-element sublists, and those again into the resultant 8-element complete list that I showed before. So you can see here, there's actually enough passes over the algorithm, or over the list, that it's not actually purely linear time. This is where you get the log n factor, because as you can see, the number of additional steps here is the base 2 logarithm of an input size of 8. So that's how you have that many subdivisions and that many kind of merges you're doing, and the size of the data you're merging is linear on whatever you're putting together. So some interesting observations about this. Now, first of all, each sublist is always walked in order. Now, this is something I mentioned earlier and why it's important. This is great because there's no random access. Also, it means you get really good cache locality. As you're walking through the data, you're only ever looking at the next one. Now, this is how CPU caches are optimized to handle that case. So it's great because it means that you don't have to you don't have to speculate and get it wrong sometimes. Also, it means that because you've now walked past part of your input, it doesn't have to remain in memory. And this is a throwback to how things used to work with the tapes, but also CPU caches are fixed size. It's great, you can now evict data that you know you're not going to use anymore. So each sublist pair is also merged independently. Now this is how you get things like your parallel implementations, because you can actually farm out these individual sublist merge operations onto other CPUs or other machines. And the other thing that is kind of an interesting observation, although it wasn't pointed out in the example, is that the sublists don't need to be the same size. Now this is part of how you can do things like building the online version of a merge sort. But it's not actually that interesting for the most part because you're wanting to keep the sublists that you're merging, you're wanting to keep them roughly the same size. As I mentioned at the beginning, merge sorting one element into a 100-element list is going to take 101 operations to sort one additional entity. Whereas, so you want to merge 2 sublists of 10. Well, then there's 20 operations to merge in an extra 10 elements. So this is something which is kind of to be considered when looking at online sorting implementations of merge sort, and why often it actually ends up just being something like an insertion sort. Now, you could get around this problem if you wanted to by doing something like making sure that you keep multiple sublists available and you're always merging ones that are the same size. Now this could be useful. There's lots of ways that in a parallel system that would actually work really, really well. The problem is that sort wouldn't be stable, because the other thing that you can see in the previous example is you're always merging adjacent lists in the input. And this is how you can make sure you didn't reorder them. Things that were relative, that have the same value, are within the new sort, don't change their relative position because you haven't reordered the order in which you're merging sublists. If you were to try doing something like only merging things that were the same size as they come in, then you might be doing an out-of-order merge. This will reduce the stability of the sort and means you can't rely on that feature. Now, something that's kind of interesting also about the the sublist not needing to be the same size, is there's what's called a natural extension to the merge sort, or natural merge sort, which is when at the beginning, instead of you walking over the input and creating a sublist for each one element, the natural extension assumes that, well, most things are already sorted or slightly sorted anyway. So why don't you instead look for what's called runs? As you're kind of partitioning the input into each sublist, you actually look at them to find out, well, how many things are already sorted in this list? Because then it reduces some of the extra overhead of, okay, merging these two elements, which are already sorted, together. Well, wouldn't it be great if you already just did that implicitly? So this is something which is really, it comes out quite naturally, that's why it's called natural. And it works really well, and the really valuable side effect of this is it means that for already sorted data or mostly sorted data, the algorithm almost entirely just falls apart into nothing and gives you the result right away. It takes very, very little time in that case. Imagine the case of an already sorted list you're trying to merge sort. Using the natural extension, you'll immediately determine that the entire thing is one run, and you'll complete the algorithm in linear time. So this is actually something which is worth doing in most cases. So I hope that that was a good explanation of how this particular sorting algorithm works. It's one of the ones I always found quite elegant because it's very simple in how it's thinking about things. It makes very few assumptions, and it's quite clear to follow. You can understand why this is a good idea, why it would work that way, why it avoids some of the extra operations that you normally have to perform in a sorting algorithm. Anyway, post any comments below or send me an email if you have any questions or another suggestion, and I'll put something together. Thanks.